I will speak about two very specific types of chemical reactivity that are vibrationally induced chemistry and the chemistry that takes place through the quantum mechanical tunneling mechanism. And I also will try to show you that we can create the conditions for these two types of chemistry to become intertwined. And since we are speaking about chemical reactivity, this certainly has also implications in green chemistry, in circular economy, in today's life of everybody. I will tell a story. And this is a story that started many years ago when we started to work using matrix isolation spectroscopy in the laboratory here in Coimbra, where I am now. And the topic, as I mentioned, is something that I can classify a new paradigm in chemical reactivity, that is the concerted use of infrared-induced chemistry. So we use a sort of spatial photochemistry where we excite vibrationally the molecules and then we follow what happens afterwards, and together with the processes that take place to the quantum mechanical tunneling mechanism. This has been recently reviewed by myself and some of my coworkers in a review article that has been published in Chemical Society Reviews, and you have the reference there. So if you are interested to go into the details of what we have been done, so I strongly advise you to read this article. So let me tell you how I will divide this talk. I will make a very short introduction, and then I will describe the main achievements in the field, starting from the very beginning. And then I will present some studies that are recent studies that we undertook in our laboratory here in the University of Coimbra, that are, what I can say, the news from the chemistry department of the University of Coimbra in this field of matrix isolation spectroscopy, IR-induced chemistry, and quantum mechanical tunneling. So why infrared-induced chemistry is attractive? Well, it is very attractive because using this approach, we can specifically deposit energy in a fragment of a molecule that then we can make to react without disturbing strongly all the other fragments in the molecule. I used to say that this is a bit like if we do a laparoscopic surgery instead of an open belly surgery. So we just try to not perturb all the body, but just focus on the things we want to change. And this an example that I have here, it's slightly different because in this case, what we do is you open new channels by vibrationally exciting a molecule. This is a photography, a scheme that I took from the literature. This is the reference here. And this was a study on diazomethane in the gas phase. And it was excited vibrationally through the antisymmetric stretching CNN vibration. It was a time-resolved experiment, and we can see that we could, the authors were able to excite the molecule and change the structure of the molecule in such a way that they open a new reaction channel that allows the molecule to take apart, to split into this carbene and nitrogen. But in our laboratory, we use essentially this approach to do something slightly different. What we want is to manipulate the geometries of molecules. In particular, we want to selectively generate conformers. This was the first series of studies we started to do, and still we are doing a lot of experiments like that. And once we can produce a given conformer of a specific molecule, we can study how the chemistry depends upon the conformation. And the example I am presenting here in this slide is one of our first studies on this subject, and the molecule is formic acid. Formic acid is a very simple molecule. It has just two conformers. This conformer is the most stable one. We use to call it cis. This is the trans conformer that has a higher energy. And then what we can do is we can selectively convert the cis conformer into the trans conformer just by infrared excitation of the cis conformer in a matrix, in an inert matrix at very low temperatures. And this means that we can do something like it is schematized here. In the gas phase, the cis conformer is clearly dominant, and when we deposit the formic acid into a cryogenic matrix, we got just the cis conformer in the matrix. And so we can shine UV light and photolyze the compound, and we can see that the main reaction products are carbon monoxide and water. But we can then convert the cis conformer into the trans conformer by infrared pumping the OH stretching vibration of the cis conformer, and then we got the trans conformer in the matrices, and then we can shine light on this form, and we realize that the major products are carbon dioxide and water. So this is one of the first reported cases where different conformers were selectively excited to give rise to different main products of reaction. And we observed later on that it's been happening for many other cases. So this is our intention also to play the game with the conformers of the reactant and then make them react specifically in a direction or the other direction. Of course, I will also speak, as I mentioned, about quantum mechanical tunneling. And here I want to highlight something that is something that has been quite relatively recently highlighted by Peter Schreiner and co-workers, that is tunneling processes are not just a minor component in chemistry. They are they are very much important in many different types of situations. And we realize that tunneling can also control the fate of a reaction. This example here, I think, is quite illustrative. So we have this third-butyl chlorocarbene that can be generated photochemically from the diazo precursor in a matrix at low temperature. And you see that this compound can, in principle, give rise to these two products. This is the product of 1,2-methyl shift, and this is not observed. And this is the product of CH bond insertion. And this is the product that was, in fact, observed. And if you note, this non-observed product is the product that could be expected to be formed both if the process would be kinetically controlled because this barrier is lower, and also thermodynamically because this product has the lowest energy among the possible products. However, this is the product that is observed, and this is strictly controlled by tunneling. Because tunneling, as you know, depends upon the height of the barrier, the mass of the particle, but also of the width of the barrier. And this barrier is considerably narrow. So the tunneling probability is considerably higher than the tunneling probability for the other competing reaction. And we got this product. So we are superseding the classic transition state theory in a process that is tunneling controlled. The general strategy we use in our laboratory to address the subjects I already mentioned is a sampling technique. We use low temperature matrix isolation. Very briefly, for those that are not aware of the technique, essentially what we have is a metastable solid solution that we prepared by depositing vapor of the compound we want to study, together with a large excess of inert material, in general argon, krypton, or nitrogen, at a very low temperature that is between say 4 and 15 degrees Kelvin in the most of situations. And then we can use this sample to do spectroscopy. And of course, we can also do some other things that we can shine light on the sample, produce photochemical events. So the probing technique we use is infrared spectroscopy. Of course, we also perform an extensive series of calculations to understand the details of the process that we are interested from the theoretical point of view. And we use infrared activation in most of the cases. Some cases also we use UV activation of the compounds in order to study the chemical reactivity of these species. So let me now briefly try to review the main experiments that that have been done in this field since the early 60s of the previous century. The first observed or reported infrared-induced conformational isomerization process was reported by Hall and Pimentel. And it's interesting because Pimentel was one of the fathers of matrix isolation technique. And they studied nitrous acid, here isolated in an argon matrix. Nitrous acid have these two conformers, and they were exciting use of broadband mercury lamp with different filters. So they were using different regions to excite the molecules, and they found out that under these conditions, they were able to change the relative populations of the two conformers. And this was particularly interesting because this was a new subject, but very interestingly, this study was not, did not get impact that we could suppose it would get because of this real interest for chemistry in general. And why was that? Well, essentially because there was not possible to achieve full control of the reaction. When broadband irradiation was used in the OH stretching fundamental, we were essentially generating a photostationary equilibrium. We were interconverting the two conformers. Of course, if you change the region we are using to excite the sample, we are changing the position of this photostationary equilibrium, but people realized that what was important would be to have the possibility to selectively excite each one of the conformers. And just after about 30 years, we came out with a quite obscure paper, I must say, that I published together with a colleague from Russia, Anatoly Kurbida, where we use some light that we made narrow in the wavelength range that we use to excite and convert the conformers of dichloroacetic acid isolated in argon and krypton matrices. So this was probably the first, or at least one of the first attempts to use narrowband excitation to try to control the reactions in a more efficient way. But as I mentioned, this paper also did not, cannot also be considered an influential paper because it was not received the light that, in my opinion, it could also deserve. The paper that appeared like the game-changing paper was published by a group in Finland by Mika Peterson, Ian Lundon, and Leonid Kryashchev, where they worked with formic acid, and they introduced the narrowband excitation using infrared light provided by tunable laser source. And in this case, what they did, let me try to explain this slide very quickly. So as I mentioned before, when you deposit in a matrix formic acid, you get the cis conformer, and this is the near infrared range OH stretching, first overtone, and we see these two bands. These two bands are due to the same conformer, cis conformer, in the as deposited matrix. There are two bands because the environment around the molecules of the formic acid in the cis conformations are different. There are two spectroscopically different matrix sites, but it is the same species. And then what we do is we can shine light, you turn the laser at the frequency of each one of these bands in site 1 and site 2, and you induce the conversion of the cis conformer into trans. And you can see here that the reaction is, of course, selective regarding the molecule. We are exciting formic acid. It is also selective regarding the conformer. We are selectively exciting the cis conformer. It is selective regarding the mode. We are exciting the first overtone of the OH stretching vibration, but it is also matrix site selective. So when we excite molecules that are trapped in this matrix site, we get transconformer in this site, and we excite the molecule. If you excite the molecules of the cis conformer trapped in the second site, the transconformer will also produce in site number 2. So this is an extraordinary selectivity that allows us to play many different games with the structure of the molecules. So these studies were then replicated in many different systems. essentially at the beginning carboxylic acids, dicarboxylic acids, and we were fortunate because we entered this game from the very beginning. So we started a partnership with the group in Finland of Markku, and we have performed many studies in different families of compounds. I give here some examples, oxalic acid, fumaric and maleic acids, malonic acids, and then we started to look to the details of the process. And there were a couple of achievements that I want to mention here. One is already something that I mentioned at the beginning. We noticed that we could use this to investigate conformation-independent photochemistry, like, for example, illustrated here again with the example of formic acid. But we also noted that in some cases, in particular when we were dealing with carboxylic acids, that we can produce one of the conformers. I'm not pleased that here the designation of the conformers is the opposite one I used in my previous slide. So when we have the most stable conformer transformed by infrared excitation in the cis isomer, you notice that once we switch off the excitation light and we let the sample in the dark, it spontaneously converted back to the most stable conformer by tunneling. So this showed us that we have the possibility to use this infrared excitation to generate higher energy species that then can undergo processes that are driven by quantum mechanical tunneling. We also realized that also in the case of formic acid, that we don't need to provide the molecule energy that is above the energy barrier for the conformational isomerization. In this picture, this is illustrated. So this represents the scale of energies. We can tune the laser at different frequencies and try to excite the molecule, exciting different modes. And this is the range of values that have been reported in the literature regarding the barrier for conversion between the two conformers, the cis and trans conformers of formic acid. And we see that when we excite with energy above the barrier, so we have a high quantum field for the reaction of conversion of the cis into the trans conformer. But even when we provide the molecular energy below the barrier, we also got the quantum field that is still quite appreciable. It is necessary to go down in energy quite a lot in order the quantum field to drop. This means that what we are doing is what we call the vibrational assisted quantum mechanical tunneling between the two conformers. Essentially, we have the cis conformer here. We are excited with vibrationally to somewhere here. So the energy barrier that separates the cis from the trans conformers became smaller and narrower, and this allows the conversion of the cis into the trans conformer by tunneling. As you can see here, also by the calculations of the wave functions we performed theoretically. In 2005, we decided to start to play games with these things, coupling, tunneling, and vibrational excitation to selectively isolate different forms in the more complex systems. One example of these studies was the one we performed on propionic acid. Propionic acid has 4 conformers. They are here represented. And 2 of them have low energy, but just one of them can be deposited from the gas phase in the matrices. And this is this form, the CS conformer. And then, of course, we can play all games we want with this species because it is isolated there. But if we turn our laser in such a way that we irradiate the OH overtone, for example, the stretching vibration of this conformer, we observe that it transforms into the CG plus minus conformer that is here by rotation around the CC alpha bond, or it produces the TS conformer by rotation about the CO bond, like it is here. And then if we switch off the laser, these species go back to the CS conformer because by tunneling, because this transformation just implies the movement of this light H atom. on the other hand, this species stays there. So we can study also this molecule into details. For example, the UV-induced photochemistry of this conformer. And then we can excite vibrationally this species using the same approach by exciting the second overtone, the first overtone of the weight stretching vibration. And this species convert into this fourth conformer and also back to the original conformer. So we have a way here to play with the structure of the conformers of this four-state system like propionic acid and study then individually the properties of each one. Of course, we played this game with many other compounds since then. In 2008, Peterson, Lundell, Aucas, and Albert Matchwood proved that we could also perform this game by doing Raman spectroscopy for the matrix isolated compounds. In this case, what they were doing is they were excited higher vibrational quantum number transitions when we were performing the studies by Raman. So the Raman excitation also would lead to vibrational excitation when they observed that the cis conformer also converts into the transformer. They were detected this in the Raman experiments. We played this game, but in a more sophisticated way, in a molecule like cytosine, for example. In this case, we use UV excitation in some cases, we use infrared excitation in some other cases, and we use also quantum mechanical tunneling to interconvert or convert the different low energy isomers of cytosine. These studies were very important, in particular the ones where we use infrared pumping of the compound, so the infrared-induced systems, because they show us that the process of energy redistribution from the coordinate that is being excited to the reactive coordinate are not statistic. So there are preferred dissipation energy, preferred channels for redistribution of the intermolecular, of the energy that we are initially deposited in the vibrational antenna, let's say like that. Otherwise, we could not expect that the efficiency of the process that we are observing here, the conversion of this conformer into that one upon vibrational excitation, would be almost as efficient as the one in formic acid. Because in this case, we can expect to have many acceptor final modes, while in formic acid we had essentially just one acceptor mode. Since the efficiency is more or less the same, it means that there is a funnel type of preferred redistribution of energy channels within the molecule of cytosine. It was more or less during this time that we came out, Peter Cherani came out with the idea of this tunneling control of chemical reactivity. In 2014, 2015, we demonstrated two other things very relevant, in my opinion. One is that we can perform this game also for weakly bounded systems. So for example, if we take the dimers of acetic acid that we can produce in situ under matrix isolation conditions, we can selectively excite this OH stretching vibration of this specific dimer and convert it into this other form where we have, instead of two cis conformers in the dimer, we have one cis and one trans conformer of acetic acid in the dimer. So using this strategy, we were able to produce almost all possible forms that you can devise for the dimers of formic, acetic, and acetic acid, including cis-cis, cis-trans, and trans-trans dimers. So the process, it is also enough efficient under this sort of molecules that contain weakly bound species inside the molecule. Another thing that, another concept that we introduced about this time was the concept of vibrational antenna, and in particular, remote vibrational antenna. This was the first case study, was 6-methoxyindole. In this case, we were exciting this NH stretching vibration, and we were inducing a change in the conformation of a methoxy group that stays far away from the region of the molecule where you were exciting. We could generalize this system, and we showed that we could interchange vibrational antennas in order to change conformations at distance in molecules. So this is also something very interesting in our opinion, and it also shows us once again that this process of vibrational energy redistribution has preferred channels that puts the energy in the reaction coordinates once they are deposited. It is deposited in the vibrational antenna. We also demonstrated that we can use higher order overtones to produce the same sort of reactions. And these also have the characteristic, still they keep selectivity regarding the matrix site. We did some studies using this approach, and the idea was to increase the range of energies that we could use to do this kind of reaction. So the idea was to overcome higher energy barriers and still continue to do the same type of processes. More or less at the same time, we, together with the group of Peter Schreiner and Gissen, demonstrated this very interesting case of two competitive heavy atom tunneling-driven reactions that we generated this benzoazirine in situ in the matrix, and then we showed that this species can undergo two competitive reactions. One is essentially nitrogen tunneling, and the other is essentially carbon tunneling. 2020-2021, we have shown that this sort of of infrared excitation can also be used to do real chemistry where bonds are being cleaved and formed. There are some examples, and here I show the example of the thiol tautomerization in thiotropolone. And here there is a slightly more complicated system where we start with a precursor that is a azide compound that we excite by UV in situ in the matrices to generate the nitrine, and then the nitrine is excited vibrationally through excitation of the OH group. And this can be excited also using ultraviolet selectively to form this compound. And this benzoazirine is the compound that then we can excite vibrationally in the OH stretching overtone. And you observe that this gives rise to this open ring reactions that generates this cyclic ketanamine. So this was I would say nowadays the old story. And in the most recent years, we were focusing something that has some improved degree of sophistication. And I want to show you a couple of examples of our later studies. One is we found out some way to control tunneling through conformational control. So tunneling, because it's a spontaneous process and it has been considered that it's now possible to control tunneling, we showed up that it is possible to control if you control the structure of the reactant species. So let me show you an example of how this can be done. So this is a scheme where we have the precursor that is an azide. We can photolyze it in situ, generate the nitrine, and this is a 2,4-mil nitrine. And we observe that once this species is formed, it fast undergoes tunneling with an average time of about 6 hours to generate this species here, that is this aminoketene. We proved that this reaction takes place by H-atom tunneling, and this was direct observation of the reaction. It is temperature independent, and it shows a large kinetic isotope effect. So no doubts that this is the things that we were observing. But then we thought about something that is, can we change the conformation of our reactant species and try to get a different product obtained by a different tunneling process? So the idea is, the concept is schematized here. We have this anti-form of this 4-mil nitrine, and then this is the product that we know we can get. So how about if we could, by changing chemically this aromatic ring here, to increase the population of this other conformer, and then maybe the reaction that we can observe is this one. So we can produce a different product of reaction. In this case, instead of H atom tunneling, we should observe heavy atom tunneling. The idea was then to place here a fluorine atom, so that it can stabilize this conformer. So this is the concept, and this is the way we use to access the seen conformers. You can see here that the populations of these conformers here are increased, in fact, when we substitute this hydrogen atom by the fluorine atom. So we have significant increase in the population of these forms. And we did that, and we looked to the structure of the deposit matrix here compared with the calculations for the different isomers of the precursor. So this was a synthesis work. And then what we observe is that, in fact, when we look to the reactions that take place by tunneling for this conformational species that we can clearly identify spectroscopically, we observe that it indeed was being converted into the benzoxazole. And this is also this is even more interesting, because we have the formation of the nitrine from the azide. This is the triplet state of the nitrine, and this is the final product. This is a singlet species, and we observe that it takes place, this process, by crossing potential energy surfaces of different multiplicity. So this is a case where we can control the product of reaction of one given molecule, that in this case is a nitrine, and we just change the conformation, and then we observe different products. So we wanted to go a little bit further on this type of experiments, and we decided to develop what we call optically controlled tunneling-driven molecular switches. And this is the concept, once again. So the system is relatively similar, but here we have OH group ortho to a center that is the reactive center that is essentially a nitrine. And the idea is, if you have a conformation like this one, this is the off state, but if we activate this form and we convert this species into that one by infrared excitation, then this species reacts because it is the on position, and by tunneling, it gives rise to this product. So this is the concept, and this is the implementation or realization of the concept. So this is our precursor, again, the azide, OH substituted, and when we photolyze it at 255 nanometers, we immediately got this product. We don't observe, in fact, this nitrine. But the idea here was relatively similar to what we did before. So we use a chemical substitution at this position. We just introduce it here, a fluorine atom in the molecule, and we increased the population of these conformers that should be non-reactive once the nitrine is formed. And that's exactly what happened. So we have in our matrix these two types of conformers, this one and this one. And when we shine light in the ultraviolet, 255 nanometers in a nitrogen matrix, we observe this species here, and then the reaction stops. We also observe this conformer here that is non-reactive, is off state, and then we can excite this conformer vibrationally, exciting the OH stretching vibration in the near infrared. It converts into this form, and it immediately reacts there. So this is a conceptual strategy to control H tunneling by optical control, optical excitation, in this case in the infrared. Now I want to present another case where we observed hydrogen atom tunneling that shows an unexpected small kinetic isotopic effect, and I want to tell something about the consequences of this observation. So this is the system. Once again, we are working with nitrines, and you can see here that we have the possibility to form the nitrine, and this nitrine, this conformation here, sorry, this conformation, it can undergo this conformation, can undergo this first tunneling reaction to this conformer, and then tunneling to the product. So this means that the conformer that I was mentioned before, when we were playing the games with infrared excitation, if we let it in the dark, with time, it also slowly converts to this species. And this is the consecutive these are two consecutive processes that have to take place by tunneling. This is fast, and this is the slow process. So what we notice is that when we replace this hydrogen atom by a deuterium, the kinetic isotopic effect is very, very small. So the factor of the rate constant is just about 3. And the theoretical models predict a kinetic isotopic effect of the order of 10 to 5. So this is an absolute discrepancy, and we have to find for an interpretation of that. And what we can see is that we were working in this case in nitrogen matrices. And we know from many different kinds of studies we performed on OH containing molecules in nitrogen matrices that nitrogen interacts, the nitrogen molecules of the matrix interact with the OH groups, both in phenols, alcohols, and carboxylic acids, for example. There is an interaction. And in this case, the interaction is such that it has to play a game in this quantum mechanical tunneling reactions. We found out the same sort of thing for these other compounds. So this is really something that is intimately related with the interaction between the matrix media N2 molecules and the OH group. This is like the sort of solvation of the OH vibration by the nitrogen molecules make the effective mass that is moving higher. And that's a very delicate compromise. But the question here that we have to think about is that most of times when we are working in solution for detecting quantum mechanical tunneling processes, we are using exactly kinetic isotopic effects. And for such a small kinetic isotopic effects, we are not expecting that these processes take place via the tunneling mechanism. So the question is, if this sort of solvation effects also takes place in normal solvation conditions in solution, this means that probably the quantum mechanical tunneling contributions to the chemical reactivity have been overlooked in many chemical reactions. So I think this is a strong implication in chemistry performed under normal conditions, and the things have to be re-examined in some cases. One of the last studies we performed was on the competitive heavy atom tunneling reactions controlled through electronic effects. The idea was, can we control tunneling reactions the same way we used to control other types of chemical reactivity by changing the characteristics of the substituents, say, for example, in an aromatic ring? Then we decided to study all these series of molecules here, where we introduced at this position different substituents with a different electron donating strength. And this is the molecule here, what we can generate in situ. And this molecule can undergo two competitive processes. This one, that is formation of the nitrine, and this one is the open ring reaction to this ketenemine, cyclic ketenemine. And then what we found out is, depending on the substituent, the relative amount of the two kinds of products was changed. Note that here this is a typical potential energy profile for one reaction, for the other one, and then here I showed two other examples. See, this is the same I showed before. This is the potential energy profile for this reaction, and here for the other one. But when we introduce the greater electron donating ability substituent here at this position, this stays more or less constant, but this changes appreciably. So this means that when we play with the electron donating ability of the substituent, we can change the path of the reactions. And you can see here that, for instance, for these substituents that are the lowest in terms of the ability donate electrons, we have essentially this reaction takes place. So because this is the barrier is very narrow compared to that one, but when we introduce it, more electron donating substituents, we get progressively importance, the second reaction starts to become progressively important because this barrier is considerably affected, and it even is dominant in the case of the last, the highest ability substituent for as electron donating. So the idea here is to show that tunneling can effectively be controlled as the other types of chemical reactivity. So just to show you what is our goal from now on, we are now developing an apparatus for doing the same thing, but in solution. So the idea is to make these things in conditions that are moving progressively towards the conventional laboratorial conditions. So this is something that we are working at the moment. This is our initial setup. We are now still developing all these things, changing the conditions, changing the solvents. That's a process that is still at the beginning, but we are working with this particular process to start. And I think that next time I would have the opportunity to speak here or somewhere else where we can meet. Eventually, we could have already developed something in this idea. The idea is now, as I mentioned, move towards conventional laboratory conditions and explore the potential of this sort of chemistries. I want to thank the people in my laboratory that were performing the experiments and also doing the calculations. I have to also thank the funding agencies. And I want also to announce that at the moment, I was appointed as the head shareholder at Istanbul Cultural University. We are now setting up a new laboratory there where we will have all the facilities also to do this kind of experiments and some other sort of experiments. And we are opening positions that will be announced very soon. Anyway, in case you feel interested to work in these fields or also in some other fields that are clearly illustrated and in the title of the air chair, please contact me directly and I will keep you informed on the way of the establishment of this laboratory. And that's all what I want to say. Thank you very much for your kind attention.
Thank you very much, Rui. Very interesting talk. If there are any questions from the audience, then please type them in the Q&A and I will be happy to read them to Rui. Okay, so we have a question by Dimitrios Anglos from University of Crete and the Foundation of Research and Technology. And the question is, what is the typical efficiency of overtone excitation? Is it enough to lead to appreciable excitation and formation of the desired product?
Yeah, I can answer. In most of the cases, if we keep the excitation, we can fully convert one species that is the species that is being excited into the other one. So it's a high efficiency in most of the cases.
Okay, thank you for this. Any other questions?
Just a comment. Sometimes the things are not so easy because we are transforming one species into the other one through vibrational excitation, and the species that has been formed is being converted back to the original one by quantum mechanical tunneling. In the matrices, we are not, it's not, the processes that takes place over the barrier are practically all quenched because the temperature is very low. So this means that we really, if we observe something that is not a result of any sort of photoexcitation, this means that with great probability it takes place through the quantum tunneling mechanism, except if the energy barriers are extremely small, such a few kilojoules per mole.
Mm-hmm. And then a follow-up question about the laser that you are using. Is it CW? Is it continuous?
Yeah, we are using neodymium lasers with a mobile system, so it's a pulse laser.
Pulse laser.
But we can use also continuous wave excitation. That's no problem.
Okay, thank you.